Okay, so today we are going to briefly discuss the idea of the DDIM inversion, which has been briefly also discussed in the previous guest lecture by Orr, and then we're gonna move on to some kind of a new topic, which is about the score distillation. So in the last lecture given by the Orr, so has discussed like lots of some kind of interesting the ideas in terms of like how we can utilize the attention the maps which is obtained from the pre-trained image diffusion models for so many kind of the image editing and some manipulation the tasks. And during her the lecture, we also briefly discussed the idea of the DDIM inversion without like having some kind of the knowing some details for that. So I'm going to briefly discuss this topic, the DDIM inversion, and then we're going to move on to the next topic. So before that, actually, let me briefly recall like what we have discussed for the DDIM. So for the DDIM, basically, we had this kind of the posterior distribution sampling the xt minus 1 from the xt and the x0. And based on that, we could basically derive some kind of the denoising the process, which is basically sampling the xt minus 1 every time, right? So in terms of like just reminding some kind of the basic idea there, so how could he also derive the formulation of the prediction of the x0 given the xt and it's basically the epsilon, the prediction epsilon theta here. Let's briefly recall the things of the that we discussed for the DDIM. So yeah, as many people posted on Slack. Yeah, basically this was the formulation, the tweet is formulation, right? So the process that we have discussed last time was basically giving the xt using the noise prediction the network. We get the prediction of the final the x0 like this, and based on that, we compute the mean of this specific distribution, and then sampling the xt minus 1 based on the information of the xt and the x0, right? So we keep repeating this process in terms of that we are basically running the denoising. And one of the special case of the DDIM was that we could basically make this process as the deterministic, which was the case that we are making the variance of this distribution to be 0. So if we set this sigma t to be 0 for all t, then what we get is that this process becomes like deterministic. So it's not basically sampling the xt minus 1 anymore, but we are basically directly calculating the xt minus 1 from the xt. So we can first compute the x0 by t, which is the prediction of the x0 for the given the xt. And based on that, we can also calculate the the xt minus 1. And then if we see these two, then we can also rewrite the formulation of the xt minus 1 with respect to the xt and the epsilon t here, right? So can you also briefly rewrite the xt minus 1 with respect to the xt and the epsilon here? It's like making this to be a kind of like one line reformulation. Did everyone get the same result with this? So here basically what we can say is that given the xt, using the epsilon, the prediction network here, we can directly compute the xt minus 1 in this specific case of the deterministic sampling when the variance is basically 0, right? So if we basically repeat this computation, then since this like epsilon prediction network is also kind of like fixed, so what we can say is that the mapping from the x capital T to the x0 is basically the fixed. So which means that if we sample any kind of the x capital T at the very beginning of the reverse process from the unique Gaussian distribution, then we're gonna say that x0 is basically the determinant. Which means that how many times like you run the denoising process, obviously you're gonna get the same results from the same xt to the same x0. So this is not the case for the DDPM. Also for the cases like when the variance is not 0, right? So if we have some kind of the non-zero variance, then we're gonna see some kind of some variation, even when it starts from the same x capital T, which is making the process to be more stochastic, right? So the question of the DDIM inversion is that, so since we know that there is some kind of the fixed mapping from the x capital T to the x0, can you also find the kind of the inverse mapping from the x0 to the x capital T? So what is basically the x capital T that resulted in basically producing the x0 from it? So that's the question of the DDIM inversion. Okay, the thing is that while the calculation from the x0 to from the xt is kind of like simple in terms of that we know the formulation. Actually, the inverse problem is basically not that straightforward because like that we are having the kind of epsilon the prediction. So for the DDIM inversion, actually there are some kind of bunch of the way in terms of like how we can get some kind of the more accurate inverse mapping from the x0 to the x capital T. But one of the kind of the simple ideas that has been basically known as kind of working well in practice, especially like when you assume that the time step, the interval of the time steps is very small, we can simply basically approximate the difference between the xt plus 1 minus the xt using the formulation for the xt minus 1 minus xt. So as you can see, like from this, we have seen the formulation of the xt minus 1 from the xt. Now we can basically have the formulation taking the difference between the xt minus 1 to the xt into this formulation, right? So the simple kind of the idea in terms like approximating the difference between the xt plus 1 and the xt is basically replacing all the t minus 1 here into the t plus 1. In terms of now we are approximating this difference into this specific formulation. So which means that since now we can calculate the difference between the xt plus 1 to the xt, we can basically run the inverse of the reverse process, right? So we can start from the x0, and then we can calculate like x1, x2, all the way to the x capital T by using basically this difference between the xt plus 1 minus the xt, right? And this is kind of like one of the examples that we are running the inversion from the x0 to the x capital T, and running the generation again using the x0 to the x capital T. You can see that now we got some kind of the results, which is like almost perfectly reconstructing the original image from the x capital T we basically produced using the inversion process. But this basically the assumption only works well when we basically use some basically very small the interval for the time steps. So which means that as we basically decrease the number of the time steps, which is basically increasing the interval between the time steps, we're gonna get some kind of results that the generation from the x capital T is not perfectly basically reproducing the results of the original the x0, right? So this is the results when the number of time step is basically the 50. So this is like the basic idea for the DDIM inversion, which is actually having lots of some kind of the applications. So one of the applications for the DDIM inversion is basically the image editing, as also Or mentioned in basically the guest lecture last time. So one of the idea for the image editing is that let's say like we are having a image and some kind of the description for that specific image. Then what we can do is that we can first run the DDIM inversion using some kind of the given the prompt for the original input image. And then now we are running basically the reverse process, the denoising the process, not using the same prompt, but using another different prompt. So in this kind of the conditional setup, we can basically produce some kind of the different images from the same DX capital T, but using the different text prompt. So this is the example that we are running the inverse of basically the denoising process using the given the text prompt for the original the input image. And then we are changing the prompt in a way that we are basically getting some kind of the new image. So this is kind of the results of like doing some kind of the image editing. So using this kind of the DDIM, the inversion, the technique, we can do some kind of the image editing without any fine tuning or any kind of the training of the neural network. This is also kind of interesting example that we are having a photograph of a face running the inversion, and then they're running the denoising again with some kind of the different prompt. Interestingly, you can see some kind of the results that we are making some kind of the images, which is basically quite similar with the input image, while basically making the character to wear the sunglasses here, and also basically changing the face like this. So this is some kind of example of like doing some kind of the image editing using the DDIM inversion. So you can try those things yourself using the Stable Diffusion in this link. So there are also lots of the examples in terms of the implementation, the code for the DDIM inversion. And some kind of the practical aspects, this is like just really practical kind of things, is that actually some kind of thing is that if you run the inversion and also the generation again using the high CFG weight, then actually you get some kind of the poor result. So this is kind of the case, like when you basically run the inversion and the reverse process again using the CFG weight of the 7.5. So as you can see, the output is not perfectly basically reproducing the input image in this case. But the thing is that if we want to really get some kind of the dramatic changes in the image editing using some kind of a new text prompt, we need to use the high CFG weights both for the inversion and the generation. So here the question is that how can we still use some kind of the high CFG weight while basically getting some kind of the good quality of the reconstruction of the input image in the inverse process? So for that, some very practical the idea, which is known as kind of the Null-text inversion, is that we are still basically running the inversion with the low CFG weight, like the weight becomes like 1 in this case. So if we use basically the low CFG weight, then we're gonna get some kind of the good quality of the reconstruction through the inversion. So let's say like the latent variables, like from the x 1 to the x the capital T, that we obtained through this kind of the low CFG weight, as kind of some sort of the pivot the variables that we want to match. And here the idea is that we are still running the inversion with the high CFG weight, like the W becomes like 7.5, while basically enforcing all the latent variables that we are getting with this kind of higher the CFG weight becomes almost the same with the pivot the variables that we obtained in this process while tuning some kind of the parameters. So let's say like this xt minus 1 star is kind of the latent the variables that we obtained with low CFG weight. And let's say this is kind of the latent variables that we obtained with the high CFG weight. So we are basically doing some kind of some sort of the tuning of the parameters in terms of that these two becomes the same. And then here the question is that what will be some kind of the parameters that we are going to tune in this case? So we can basically tune many things. We can basically just like tune the noise prediction the network, the entire network, or the many other things. But the idea that the people are proposing in this case is that instead of like the tuning the entire noise prediction the network, we only tune the Null-text the prompt. So we discussed in the CFG that there will be some kind of the Null-text, some kind of the prompt, which is fed as some kind of the case for the unconditional the case, right? So by just only tuning this kind of the Null-text prompt, while basically matching these two, we can somehow try to basically match the trajectory obtained by the high CFG the weight here to be the same with the trajectory that we are obtaining with the low CFG the weight. So this is kind of example that when we simply just use the high CFG weight for the inverse and the generation the process, we get this kind of the different outputs. But if we still use this, use the high CFG weight while basically optimizing the Null-text prompt, then we get some kind of the results which is like way closer to the input image in this case. Does it make sense? So these are also some kind of comparisons with, of course, some different ways of like doing some kind of inversion. So compared to so this is kind of the case that we are running the DDIM inversion with the high CFG weight without doing any kind of fine tuning. So you can see that now the output looks kind of close to the input image, but still having some different colors in the word on the backside, right? But if we basically fine tune the null-text prompt, we get some kind of the much closer results with the input image. So does this mean we need to tune the null-text prompt for every image? Yes. So you basically need to tune the null-text prompt for every single image that you get. Yeah. So this is a good question. So, but once you basically fine-tune the null-text prompt for the given the input image, you can get some kind of like much better results in terms of doing some sort of editing. So those are all the examples that you are running basically the DDIM inversion with the high CFG weight for the given the input image, and basically applying some kind of the prompt in terms of we are getting some kind of different the editing the outputs like this. These are also some more examples. So there are lots of actually there are also more ways to doing this kind of the DDMD inversion, and also there are also lots of the applications for the DDM inversion. So you can also see some of the examples in at the end of like these lectures as well. So this is also like one of the examples, like doing some kind of the zero shot image editing. So without doing any kind of so obviously like this is the case that we are involving some kind of the fine tuning of the null-text prompt. But after doing some like small fine tuning, you can get some kind of results that we are doing some kind of the bunch of some kind of the image manipulations. Any questions on this? Okay, so then let me move on to the main topic for today's lecture, which is about this code distillation. So this is like more important topic for today. So actually what we have discussed so far was mostly about some kind of like playing with some kind of images, right? So while the diffusion models were not only for the generative models, only for the images, that actually diffusion models can be applied to the many different types of the data. So we also have seen a bunch of the examples in the first lecture of this class. Like this can be also applied to the music generation, so can be applied for the molecule structure generation, or this can be also applied for the human motion generation. So there can be lots of the applications of the diffusion models in terms like making some generative models for the bunch of the modalities of the data. So what we are going to typically see, especially see for today, is that we are going to see some kind of examples for the 3D generation. So there has been lots of some kind of the examples of like applying the diffusion models for the 3D generation. So as you can see here, there are some kind of works, so like making some kind of the point cloud here, or making some kind of the voxels here. And after doing this kind of some bunch of the iterations, like making some new diffusion models, actually we could get some like quite good quality of the 3D outputs in terms of like producing those things using the diffusion models. So these are also one of the examples of like diffusion model, the outputs, producing some kind of the 3D shapes. And as you can see, the output is kind of good in terms of like, capturing some fine details in the 3D geometry, in terms of like having some all the thin the parts or some kind of the structures in the 3D shapes. But the problem is not in the kind of the technique of like in terms of how we implement the diffusion models, but actually the challenges are not only in the techniques of the generative models, but actually in some kind of the deficiency of the data. So when you basically consider like using the diffusion models in terms of like making generative models for some kind of the new types of the data, the issue is that there are not that kind of like many scale, like the large scale kind of the data set. So especially like when you compare the scale of the data set with the scale of the image data set, for the image data set, as we have seen in the previous lecture, there are like very large scale the data set, like having some billions of the kind of the pairs of the text and the images. One of the well-known kind of the data set for the image was basically Leon, which has been public so far, but which is now not basically prohibited to use some kind of commercial purposes. But for this data set, we are having like 5.8 billions of the pairs of the text and the images. But the biggest kind of the data set for the 3D, the known kind of data set for the 3D is still kind of the 10 million, which is basically like way smaller to scale compared to some kind of the image data set. So this is kind of like some kind of the lack of some kind of the large scale data set is basically kind of the problem in terms of like making a generative models that can really produce very diverse some kind of the outputs. So when it comes to like producing this kind of some sort of the imaginable some 3D shapes, like if we think of like making some kind of the cloak, like wearing a sweater, and the ghost like eating a the hamburger, those are not some kind of something that we can expect to see some kind of the 3D models in some kind of the online the repositories. So these are really some kind of something that we can imagine. But it's really hard to expect that we're going to have some these kind of the examples in some kind of the given some 3D model the data set. But if we basically consider like a way bigger the data set, like some billions of images, then there might be this kind of some very interesting some kind of samples there. So here the question is that like even without like having some this kind of the large scale the data set that can cover like all the diversity, all these 3D shapes, how can you make some kind of the some sort of the generate the model that can produce like very diverse some 3D shapes? And here the idea is that without basically relying on having some kind of the large scale 3D data set, what we are going to do is that we are going to some kind of like do some kind of some distillation of the knowledge from the image diffusion models. So what does this mean is that we are going to basically extract some information that has been learned by the pre-trained image diffusion model in terms of like not only producing some of the images, but some other types of the visual content, which can be 3D or some kind of the vector images or some kind of the mesh textures, panoramas, many other things. So here the question is that how can you basically extract some of the knowledge learned by the pre-trained image diffusion models to produce many other things? So this is kind of the main topic that we are going to discuss today. Yeah, so these are some examples. And for that, I'm going to very briefly start to basically introduce some kind of the basic ideas for the 3D reconstruction. So this is kind of the basic in terms of like seeing like how we can do some kind of the 3D generation. So the basic idea for the 3D reconstruction for the multi-view images is basically that we are having some kind of the collection of the images that are basically seeing some kind of the showing some same 3D object or the scene, 3D scene, and then also taken from the all different viewpoints, and basically reconstructing the 3D information like this. So I guess many of you might hear about the technique called the NERF. So this is basically the basic technique, which is doing this kind of the 3D reconstruction from the multi-view images. So as you can see, the output looks very good. So this was kind of like very recent the advances in terms of like achieving this kind of the high quality 3D reconstruction outputs from the multiple images. And I guess some of you might also know about the technique called the Gaussian splits. So this is like another the technique which is also doing some kind of a 3D reconstruction from the multiple images. So the video now you are watching is not some kind of the video taken from the real scene, but this is kind of some kind of the synthetic video, which is like obtained by exploring some kind of the reconstructed 3D scenes. So if I play this again, like playing some kind of video game, now we are basically moving around some kind of some reconstructed 3D scenes. So you can see that there are some kind of some black parts in the top, which is basically the unreconstructed some kind of regions in this 3D. But you can see that now it really looks like we are navigating these 3D scenes, right? Because this is really the process that we are rendering these 3D scenes into every single the camera frame into the real time, and the quality also looks very good, right? So this is like kind of like one of the very surprising the technique that we can do this kind of the like very fine accurate 3D construction from by just taking some multi-view images, right? For those kind of 3D reconstruction, there has been like lots of the advances for that. So if you are also interested in some more details for those kind of 3D reconstruction techniques, I was also teaching the other course, which was the machine learning for 3D data. So you can also check out that course to learn more the details. I'm also going to teach the same course next spring semester. So you can also take that course. But without basically discussing any details about this 3D reconstruction, the basic kind of thing is that we are going to have some kind of some 3D representation. So there can be some multiple options for that. But basically, like one of the well-known examples for this 3D representation will be basically this like the nerve, which is basically having the implicit representation. So in this case, like we are not having any kind of some explicit information, but what we can get is that if we basically want to query any of the point in the 3D space, let's say like we are basically shooting a ray into the 3D space, for any point over the ray, we can basically retrieve the information of the RGB, the color, or some kind of the density of some kind of the 3D the occupancy from each of the point by basically feeding the point information into the neural network and then basically getting this output as kind of the some output of the neural network. So which means that the whole the 3D information is basically encoded into the neural net. So the 3D information is basically represented as kind of the neural network the function. So this is the case that we are having some kind of the implicit representation, or we can also consider having some kind of the more explicit representation. So this is the another case that we are representing the entire 3D scene as some kind of the collection of some kind of some blobs here, right? So those blobs are called the Gaussian splat, some splat kind of things. By having this kind of some Gaussian displays, we can basically convert this kind of some explicit representation into this kind of defined images through the process that we call the rendering. So these are some kind of examples in terms of that we are having some kind of some representations of the 3D. So which means that we are having some kind of the parameters that we can represent some kind of the 3D object at the 3D scene. And then for those kind of a process, typically we're going to also have the process which is called the rendering. So rendering is basically the process that we are having some kind of the 3D scene here, which is represented as the theta here. And then mapping this 3D scene into the image from the specific viewpoint C here. So if you took the computer graphics course, is there anyone who took the computer graphics course? So, yes. How many of you took the computer graphics course before? Yes, no? Just raise your hand if you took the computer graphics course before. So if you took the computer graphics course, like you see that actually the computer graphics is like all about doing some kind of the rendering, how we can basically do some kind of the projection of the 3D into 2D. So we're gonna basically assume that there is some kind of the given the rendering function, which is basically some kind of the differentiable the function mapping the 3D representation into the 2D images from the specific viewpoint. So given this kind of some 3D representation and also the rendering function, what we can see as kind of some sort of the 3D reconstruction the process is that 3D reconstruction is basically some kind of the optimization the process that we try to match the rendered images into the given images. So let's say like we are having some kind of the n number of the viewpoints here. For each of the viewpoints, we are having some kind of some given images, right? And what we do is that every time, like for each of the viewpoint, we basically render the 3D scene into the image and try to basically match this rendered image into the given image by minimizing this like L2 loss. And then we are running the backpropagation through the 3D representation, the theta here, in terms of that we are minimizing this loss for the every single viewpoint. So in a very high level, this is kind of the everything about this 3D reconstruction. Basically nothing but just like, rendering the 3D representation into each of the viewpoint, minimizing the outer loss and running the backprop through the 3D representation. So this is basically the basic idea for the 3D reconstruction, while there are tons of the details in terms like how we can exactly do this. Right? But the high level idea is pretty simple, right? Render 3D scene into the 2D images, match the images into the given image, and running backprop through the 3D representation, right? So given this kind of the basic idea for this 3D reconstruction, obviously there are lots of the challenges, right? And one of the challenges like people are basically investigating was basically how can we basically reduce the number of the images to get some kind of the accurate 3D the reconstruction outputs. So the thing is that obviously, like when you have some kind of the more number of the images from like very different kind of the viewpoints, we will be able to get some kind of the more accurate outputs, right? But here the question is that even with some very few number of images, like when you just take like 10 images, like 5 images or the 3 images, so like when you have some very small number of the images for the same object or the scene, how can you still get some kind of the good quality of the 3D reconstruction? So that's kind of like one of the questions in the 3D reconstruction. So actually, the obvious thing is that if we have some like very small number of the images, it may not be sufficient to get some kind of the good 3D reconstructed outputs. So for those kind of the cases, basically we will need to use some kind of the extra information. Right? So here the question is that what sort of the extra information that we can use. So one of the ideas in terms of like using some kind of the extra information is to use this kind of the text image model. So one of the kind of the representative example for the text image model will be clip. So I guess also many of you might hear about the clip, but clip is some kind of the one of the foundation model, which is basically linking text and the image. So the role of the clip is that if you have a pair of the text, some text description and also the image, then the clip can give some kind of score in terms of like how well these two are basically aligned with each other. So this is the example that we are having the text of a beautiful painting of a dog riding a dolphin, and we are having the image for that. And clip is basically giving the kind of score of the alignment between the two text and the image. And the idea for this kind of the alignment is like extremely simple. Basically, what we are doing is that it's basically nothing but having some kind of the encoders, both for the image and the text separately. So the role of the encoders is that they are basically mapping the given the image and the text into the latent space, which is basically the hypersphere space. So you can think about that there are some kind of the imaginary, some kind of the sphere in the high dimensional space, and then we are mapping both the image and the text into the latent space. And what we want to do is that we want to say that the distance over the latent space becomes some kind of the similarity between the given the text and the image. So as basically there the distance is basically closer in the latent space, which means that these two are basically aligned more. As the distance is basically far, these two are basically not aligned. So we are basically encoding basically the text and the images into the latent space in a way that the distance in the space can give some information about basically the alignment between these two. So clip has been basically trained in this way using like 400 millions of the text image pairs. So this is basically like very well known the foundation model giving some kind of a similarity between the text and images, right? So basically what we can do in terms of like using this clip as some kind of the extra information in the kind of the 3D reconstruction. So in addition to basically measuring some kind of the alto loss for the given the images from the specific viewpoints, what we can do is that basically we know that this object should be bulldozer, right? So we are not only basically minimizing the alto loss between the rendered image and the given image, but we also basically maximizing the alignment between the text bulldozer and the rendered images. So let's say like we render the images from render this 3D object into some kind of the random viewpoints, and we can now measure the distance between the rendered image with the text prompt we have, right? Then we can also consider like maximizing this kind of the alignment, basically minimizing the distance in the clip embedding space as kind of some kind of the extra the loss function. So this can be basically one of the way that we can utilize this kind of some clip the embedding space in terms of basically improving 3D reconstruction, especially like when you have some very small number of the input images. It is clear. Also, one thing what we can do is that we can measure not only the text to image distance, but we can also consider measuring the image to image distance as well. So when we basically do not have any kind of text description for the object that we are reconstructing, we can just like measure the distance between the image that we have from some other the viewpoint with some kind of image that has been rendered into the different viewpoint. But here the thing is that since clip has been trained to basically give some kind of the alignment between the text and the image, basically, from whatever kind of viewpoint we render this 3D object, basically the bulldozer will be bulldozer, right? So whether basically we render the bulldozer from the front viewpoint or we render the bulldozer from the side viewpoint, basically those images will be the images for the bulldozer. So we can still measure basically the distance between the rendered images from the different viewpoints in terms of basically checking whether those are all the images basically representing the same bulldozer, right? So the idea for that is that even without having any kind of the text description, we just like render the images from any arbitrary viewpoints and basically map those images with and also the given the images which are basically from the different viewpoints and checking whether they are basically at the same point in the clip embedding space in terms of basically minimizing the clip distance to check that whether they are basically representing the same object. So this is basically one of the ideas in terms of like we are utilizing the clip, the text image, the foundation, the model for this 3D reconstruction. Make sense? So this is like the case of like the few shot, the 3D reconstruction. And the interesting thing is that we can go into the more extreme case. The more extreme case is that now we can consider the case that there's no image input. Without having any kind of the input image, let's think about that we only have some kind of the text prompt, some kind of the description of the object that we want to reconstruct. Then without basically minimizing any L2 loss between the rendered image and the given image, we can only basically minimize the clip distance between the rendered image and the given the text prompt. So this is actually the same the process of the 3D reconstruction, but we only change basically the loss function. The loss function is not the L2 loss, but basically the clip distance between the rendered image and the given the text prompt. So by minimizing this loss function, now we can do some kind of the 3D reconstruction without any input images, but just with some kind of text prompt. Then now we can see that this is not a reconstruction anymore. Now this becomes a 3D generation because there's no image information, right? So these are some of the examples of like doing some 3D generation in this way. So as you can see, the output looks some kind of interesting, like it's not very realistic, but we are seeing some kind of the interesting examples. Like, so this is like this was like one of the famous examples, like a archer in the shape of the avocado. Then you can get those kind of results. So as you can see, the output is not very realistic, but we are getting some kind of something in terms of like getting some 3D outputs. And this was the first example, like making some 3D generated models without having any 3D information, but only using the 2D information. So we only use the text image, the foundation model to some kind of the 3D generation, right? So this was some kind of the background in terms of doing some 3D generation using the 2D priors. Then here the question is that instead of like using the clip, can we also use some kind of the pre-trained image diffusion models for the same task? So this is kind of the main topic. So this is kind of the interesting because like basically the diffusion model is basically some sort of the generic model. So the role of the generic model, especially like for example, like for the text to image generation, is basically taking the text as the input and then generating image as the output. But here, basically, what we need is basically not the generator, but basically discriminator. As we also have discussed in the GAN, the role of the discriminator is not producing the image as the output, but taking both like texts and the image as the input and giving some kind of score of the alignment, right? So basically, their roles are basically not the same. The role of the generator is like producing the image as the output, but the role of the discriminator is taking the image as the input and then giving some kind of the score of the alignment. So here the question is that how can you convert the pre-trained image diffusion model as some kind of one of the discriminator in terms of that we can utilize this kind of score in this 3D reconstruction. So this becomes a task for the 3D generation using the pre-trained image diffusion model. Is this clear? So we're gonna basically discuss the idea in terms of how we can basically convert a pre-trained diffusion model as the discriminator. So this is the idea which is called as core distillation desampling. Actually, the idea is quite simple, but we're gonna also discuss some more details for that. So here, basically, the idea is that how can we reverse a pre-trained diffusion model to measure the alignment between the rendered image and the given the text prompt. And for that, we're gonna basically see basically the loss function of the DDPM and the DDIM again. So if we see the DDPM and DDIM, the loss function, it looks like this. And we can basically, instead of having the xt here, we can basically compute the xt from the given the x0 with some kind using some default jump here, right? So what we can basically assume is that if the training of the diffusion model has converged, then we obviously like the loss for the data point, real image, the x0 will be close to 0, right? While basically the loss for the some fake image, the unrealistic image for the x0 will not be close to 0. So here the very basic idea is that we are using the loss function this as some kind of the measurement of the alignment between the given the image and the given the kind of text prompt. So now instead of like having some kind of the L2 loss or the clip the distance, we are going to calculate the gradient for the back propagation in this way, which is basically nothing but just like taking the gradient for the loss function that we have used in the diffusion model training. So let's see this like step by step. So basically, this is basically nothing but exactly the same process with the DDPMD training. So what you can see is that we are basically having some kind of the rendering of the 3D representation from the specific viewpoint see here. So this becomes this, and this becomes the same with the x0 here, right? Once you have the x0 here, we're gonna basically perform some kind of the forward jump by adding some kind of the noise, right? So now we can see that this entire part becomes the xt, which is the output of the forward jump from the x0 here, right? And then we are going to basically predict the amount of the noise that we added using the noise prediction network here. And then we are calculating the alto loss between these two and running the back propagation all the way to the 3D representation, the theta here. So you can see that this is basically nothing but we are just using the same loss function that we have used for the diffusion model training as some kind of the measure of the alignment between the given the rendered image and the text prompt y here. So this is it. I mean, this is very, very simple, the idea. But one very practical thing here that you can actually ignore for many of the cases is that the people who originally introduced this idea has proposed to basically simplify this computation in terms of reducing the amount of the memory to be used. So if we basically see this kind of the gradient of the L loss here, then we can basically decompose this into the chain rule, basically having some kind of the multiple decomponent of like computing the gradient, right? And you can see that actually this is the part that we are computing the Jacobian, basically the gradient of the with respect to the xt for the noise prediction the network. And since this function, the noise prediction the network is basically a large function with lots of kind of the parameters, actually this computation will basically take some time. Actually, it actually takes some kind of the lots of some kind of the GPU memory. So practically, what we can do is that we can basically ignore the computation of like this part. And people have shown that like when we also omit the computation of like this noise predictor, the Jacobian, it still works well, while basically using much less kind of the GPU, the memory. So this is basically the final version in terms of like, the gradient that we are calculating for the backpropagation. But as you can see, like this is basically nothing but we're actually calculating the backpropagation from the loss function that we have used for the diffusion model training. And this is some kind of the results, like showing the kind of the effectiveness of like dropping the noise the predictor, the Jacobian. So this is kind of the original version, like not using the Jacobian of the noise prediction network. Looks okay. And when you also use the Jacobian, there's no big difference. So you can also play with this, like how much basically dropping the noise prediction, the Jacobian is really affecting the final the outputs. But actually, when we tested those kind of cases, actually what we found is that this kind of giving some kind of similar the outputs. And also the computation is time is also kind of similar. But when you start to compute the neural net, the noise prediction, the Jacobian, it starts to take some kind of the more the VRAM, the memory. So that's kind of practical issue, like why we are not basically calculating the noise prediction, the Jacobian. But other than that, actually, you can see that this is basically nothing but using the loss function of the diffusion model training as kind of the measurement of the alignment for the text and the image, right? And why is it called the score distillation desampling? So this is basically the example that we are distilling the knowledge learned by the pre-trained the diffusion the model into the form of the score, right? So we basically use some kind of the information of this score to basically see whether the rendered the image from the 3D representation looks realistic or not. So in this way, basically we can generate some kind of the not only the 3D but many other things. So actually also this is kind of a special case that we are basically generating some kind of the some visual contents that can be rendered into the images. And as you can see, this idea can be used not only for the 3D representation, but actually for many other things that can be basically mapped to the image, right? But the reason like why we are not running the reverse process about running the score distillation and sampling is that because the output that we are generating is not represented into the form that we used for the diffusion model training. So for the diffusion model training, we have used the images which are represented as some kind of the per pixel colors. So actually we can use the same idea of like score distillation sampling for the image generation as well. But this is kind of like the special case that the images are not represented as some kind of the per pixel colors, but some kind of the 3D representation that are basically mapped to the images through the rendering the process, right? So for those kind of the cases, like we cannot directly generate some kind of the such kind of 3D representation because our diffusion model has not been trained to produce those types of the data, right? But we just basically have some kind of the mapping from the output that we want to get into the images, which is basically something that diffusion model can generate. For those kind of cases, like we can consider basically applying the score distillation sampling in terms of that now we are doing some kind of the sampling, not through the reverse process, but just like iteratively applying the gradient descent through the representation. So you can think about those kind of some applications in terms of like you are having some kind of a pre-trained diffusion model, which was trained to produce some specific types of the data, but you want to there is something else, which is like not having the type or same representation, but they can be basically mapped to the data into the form that we know, using some kind of some rendering the pipeline, some rendering the function. And this function is basically the differentiable. For those kind of the cases, like we can consider not making a diffusion model dedicated for that specific types of the data, but using this core distilling and sampling in terms of like distilling the knowledge learned from the pre-trained diffusion model to produce some different types of the data. So this is kind of some of the examples, and yeah, some examples of like 3D generation using the SSD pipeline. So as you can see, the good thing is that without like having some very large scale the 3D data set, having all the diversity with like the ghost like eating the hamburger or many other things, now we can produce those kind of things because our image diffusion model, which has been trained with the 5 billions of the images, have this can cover this level of the diversity. So this is kind of the good thing in terms that we are distilling the knowledge from the very big the diffusion models. And some more examples of the 3D reconstruction. So as I said, like this idea of like score distillation sampling actually can be applied to the many other types of the visual contents, while basically using the same some image diffusion models like the stable diffusion. So this is like one of the examples that we are now generating the vector images, which can be also rendered into some kind of the some rasterized images as well. And also this can be applied not only for the 3D generation, but also for the 4D generation, 3D plus some kind of the motion, as you can see here. And this is also one of the examples like doing some sort of the 3D mesh editing. So for the cases that we have some sort of 3D meshes like this, we can do some kind of the user interactive some editing like this, like just pulling some of the parts of 3D objects, which will basically break these 3D shapes like this. And then we can define this kind of the deformation using the SDS with some kind of pre-trained image diffusion model in terms of that the rendering also becomes more realistic like this. So the part of the first assignment will be about basically implementing this kind of this core distillation sampling for some of the some simple the applications. But I also strongly recommend you to basically check out this library, which is basically providing everything about the using the SDS for the 3D generation, and you can also play with that in terms of doing some 3D generation or many other things using this idea. But there are also some kind of the some limitations of this idea. Can you see what will be some kind of the failure cases when you only use the 2D priors for the 3D reconstruction, 3D generation? Any thoughts? So these are some of the examples of like 3D generations using the 2D images. Can you now see some kind of the failures cases using doing some 3D generation using 2D priors? So these are one of the very well-known failure cases in terms of that while the output looks kind of okay for each of the specific view, if we start to do some kind of see the 3D from the different views, we can see that actually the output doesn't make sense in terms of that we are having some multiple faces for the squirrel here, right? Also same for the Pikachu and also here, right? Having some kind of the multiple faces. So these are some of the examples that we are seeing some kind of the some realistic, some sort of the images in some extent for many specific views. But if we start to see all the 3D outputs from the different views, then we can see that actually the outputs are not consistent, not basically making sense in terms of that we are having some kind of the multiple faces from different views. So this is the problem which is called the Janus problem, like having some multiple faces of different views. And this is basically happening because like there is basically no priors for the 3D shapes themselves, but it's more about basically using the 2D priors. We only have the information about the 2D images. So it tends to make some kind of the realistic images for each of the views. But when you see the 3D outputs, the output may not be realistic, as you can see here. So this means that we need to somehow consider in terms of combining, not only basically using some kind of the image information, but also using the 3D information to get some kind of the more realistic 3D shapes as well. And another some kind of the failure cases of the SDS is basically in that there are actually many of the examples that it fails to basically converge into some kind of the outputs. So especially like when you use some kind of the low CFGD weight like this, you get basically empty kind of things. So in terms of like improving the convergence of some this kind of iterative, some kind of updated scheme, what we need to do is that actually we need to increase the CFG weight up to very high number. So when you use some basically very high the CFG weights, it becomes much easier to get some kind of some convergent kind of outputs like this. But using some kind of the high safety weight also means that we are losing the diversity. So as we basically increase the high safety, basically increase the safety weight, whatever kind of the seed point we use, basically we are getting some kind of the almost the same outputs. So there is basically some kind of some trade-off in terms of like as we increase the high safety weight to get some kind of the better the convergent outputs, we can also lose some kind of the diversity. So there also has been lots of the ideas in terms of improving the SDS. Like also one of the ideas for like improving the SDS is basically not using the random noise epsilon t here, but we are also using some kind of the dedicated the random noise here in terms of basically training the LoRa here. So if I just briefly explain this idea, it's basically nothing but now generating the 3D things, not the only single one, but multiple 3D things like this. So while basically generating some multiple 3D objects here, we are not only basically updating those things using the SKSD loss, but we also fine-tune the noise pretty network using LoRa here. And then we are replacing the epsilon t here into some kind of the epsilon that we are predicting using the LoRa. In terms of this will basically give some kind of the better idea in terms of like what we need to update in the 3D representation. So you can also check out those kind of the ideas. And actually, there are some kind of the more interesting thing in terms of like how we can connect the DDIM, the reverse process with the SDS. So we're gonna get into more details about the connection between the DDIM reverse process and the SDS next Wednesday. And also we can extend this idea of like score distillation sampling not only for the generation, but also for the editing as well. So we're gonna also get into the idea of like how we can extend this idea for the editing in the next Wednesday. So this is it for today. Any questions on this? Okay, then I will see you next Wednesday. Thank you.